We're going to start our 11.2 notes, which are about chi-square two-way tests. Two random samples of M&Ms were taken, one sample of milk chocolate and one of dark chocolate, to answer a burning question uppermost in the minds of all true chocolate lovers. Is the distribution of colors the same for dark and milk chocolate M&Ms? So we see here a sample of 334 dark, 386 milk chocolate M&Ms, and the number of colors, brown, yellow, red, blue, orange, green, in each, a total of 720 in the samples, the two samples together. Now, let's look at how we would compute the expected value by hand. Let's say the question here is the distribution of colors the same, so we see different distributions here. But if we were expecting the same proportions of every color in both dark and milk chocolate, we would be looking at the overall proportions. In other words, overall 123 out of 720 are brown. So we would say, what is that proportion? 123 over 720, which turns out to be about 17%. About 17% brown overall. Then I'm going to apply that to the total of dark chocolate. In other words, if this is the proportion of brown, then how many brown would I expect? Well, it would be that proportion times the total number of dark chocolate M&Ms, which turns out to be 57.06. I'll just make this 57.1. For the milk chocolate, then we would be looking at the total of the milk chocolate. We would have 123 out of 720, or about 17% browns, and then apply that to the total number of milk chocolate, and we would get the number of browns that we would expect. That turns out to be about 65.9. Now I could go through that same thing and do 113 out of 720 times 334 and 386 to get the expected number of yellows, and I could go through that whole process for all of those. However, we're going to be using technology to find our other expected values. You should be able to find them by hand if necessary. Let's take a look at our hypotheses. Our null hypothesis is that the distribution of colors is the same for both populations. Notice that I specifically included for the populations of dark and milk chocolate M&Ms so that I know that my hypothesis is specifically about the populations. And then we would say, of course, for the alternate, that the distribution of colors is not the same, or that it's different. Looking at our conditions, so this is our state, our plan now, is we have two random samples, two independent random samples of M&Ms. The 10% condition, it's reasonable to assume that for both samples, each sample is only 10% of the population, that there's at least 3,340 dark chocolate and at least 3,860 milk chocolate M&Ms. And then the last one is that the expected counts are all greater than or equal to 5. And to show this, we have to actually calculate them and write them down. And we're going to do that using technology. And so we're going to do that using the chi-squared two-way test on the calculator. Okay, so how do we do a chi-squared two-way test on the calculator? And I'm going to go ahead and clear off what I've got here. To do this, we have to make a matrix of the different M&M counts. To make a matrix, we go to this button right here on the calculator. We choose the 3x3 matrix because that can be changed. In this case, we want a 6x2 because we have 6 different colors for 2 different populations. We have a 6x2 array of numbers. And then we type in those numbers. I'm going to go ahead and pause the video and let you type them in, but basically you type and you push tab and then you keep typing in all those values. So I'm going to go ahead and pause and do that. Now we'll use control variable to store that to a variable name. I'm just going to call it M for M&Ms. You can name it with a longer name if you want to. I'm going to go quickly through this test because there's a separate video on how to do this stat test if you need a little more information. My observed matrix here is matrix M. Push OK, and there I have my values. So I'm going to fill those in. But if I want to find, the expected results, the expected numbers, I can go to the expected matrix under the variable button, go to stat expected matrix, and I get all the expected counts, and I can copy those onto my table. So once again, I'm going to pause, put all those into the table. You do this. It's okay to round to 1 decimal place, but don't round to the nearest whole number with expected counts. It's definitely, expected counts are not necessarily going to be whole numbers. So we do see that the expected counts are all greater than or equal to 5. Now, writing down the chi-squared value that we got from the calculator, 56.62, the p-value was 6.05 times 10 to the negative 11th, practically 0, okay, very small number. And the degree of freedom is 5. I will, in a separate video, I'll explain why the degree of freedom is 5. It's the number of rows minus 1 times the number of columns minus 1. That's how you figure out the expected value for the degree of freedom for a two-way table. So this is 6 minus 1 times 2 minus 1, and that's why we get 5. I'll explain why that's true in a separate video if you are interested. I do want you to show a little portion of the formula. Remember that the chi-squared formula is the sum of all the observed minus expected values squared over the expected value. So in this case it would be, if we look up at the table, our first one would be 78 minus 57.1 squared divided by 57.1 plus, and go all the way to the last cell in the second column. We would have 60 minus 70.8 squared all over 70.8, and that equals 56.62. Now remember, the chi-squared value can vary depending on how many cells of data. We have 12 cells of data, so we have a fairly large value, but even for 12 cells, that's very large. We have a very small p-value. So our conclusion is, since the p-value is approximately 0, is less than any significance level, alpha, we reject the null hypothesis. In this case, we have strong evidence that the distribution of colors is different for dark and milk chocolate M&Ms. Now, whenever we reject the null hypothesis in a chi-square test, we need to do a follow-up analysis. I think maybe it's called extended analysis in your book, follow-up analysis, extended analysis. What we need to do is we need to look at which of these chi-squared cell values or chi-squared components. This is known as a chi-squared component. This whole computation right here. We add up 12 of those to get our chi-squared value. Each one of those is a component referring to a specific cell. Which one of those are the largest? Once again, we can go to our calculator and we see that there's a component matrix under the variable button. Go to our component matrix, push enter, and you can see all the different chi-squared cell values. And we notice that we have 4 of them that are particularly large, particularly these two. These correspond to the blue M&Ms and these to the brown M&Ms. So when I see those values, my largest values here, I'm going to go back then and look back at my table and say, okay, the ones I need to talk about are the brown and the blue. All right. What I notice is that there are a far higher number of brown in the dark chocolate than expected, and a far lower number of blue in the dark chocolate than expected, and then of course vice versa for the milk chocolate. And the milk chocolate has a lot less blue, a lot more blue and a lot less brown than expected. So I want to comment on which colors were the most different and how they were different. So I'm going to write most noticeably there were far more brown and far less blue than expected in the dark chocolate. And vice versa for the milk chocolate. I suspect it's because they want the dark chocolate to look more chocolatey, so it has more brown in it. Okay, so this is called a chi-squared test of homogeneity. There's also a chi-squared test of independence, which have exactly the same computational values, but the way we write about them is a little different. So the next test we'll look at is a chi-squared test of independence, and then we'll talk more about the difference between the tests in a future video.